Hi guys, I'm Kevin.
And I'm Emily.
We're here today to talk to you guys about carbon sequestration.
So to begin, a little overview about what carbon capture and sequestration actually is. It is a technology that can be used to reduce our global CO2 emissions. And how this is done is it's a three-step process. First, the carbon dioxide is captured from industrial power plants. Then it is compressed and transported to a site where it can be stored in one of three different ways.
So carbon is captured in one of three different ways. Pre-combustion, which is where the CO2 is captured prior to combustion. Post-combustion is when the CO2 is captured after combustion, and oxy-combustion is where oxygen instead of air is used to burn fuel, and then the CO2 is captured after the combustion process. Once the CO2 is captured, it's compressed, and then it is mainly transported through pipeline and alternatively through ships. And this is similar to the transportation of other fluids such as natural gas and oil. Also, the last part of the CCS process is the sequestration of CO2. So mineral sequestration is when CO2 is dissolved with water, which forms a weak carbonic acid. Over time, the weak carbonic acid turns into a solid carbonate. For ocean sequestration is when CO2 in ocean water is injected deep into the ocean. At this depth, the solution is denser than water and remains deep down in the ocean floor. However, the environmental impacts of this method of sequestration is great, in that it is not mainly used as a method of carbon sequestration. The last method of sequestration is subsurface reservoir sequestration, where CO2 is injected into the subsurface for enhanced oil recovery or just sequestration.
So a little background on CCS. First, CO2 began to be mainly used in 1970 for enhanced oil recovery. I'll talk about this a little bit later. Then in 1991, the Norwegian government was the first government to impose a tax on CO2 emissions. And then from 2000 to 2008, a carbon capture project was launched, and it was a combined effort of 8 of the world's leading energy companies to not only research and improve the technologies, but also spread knowledge about carbon capture and sequestration. And then in 2008, in Germany, the first clean coal power plant was engineered with a carbon capture and sequestration technology implemented as well.
So, that's you.
Okay, so for our first study, we looked at a location in northern Italy. This was part of a European CCS initiative to further research, and one of their potential storage sites for CO2 was in Italy, and it was determined through seismic survey that it was the reservoir itself was surrounded by a large number of complex thrust faults. So what they did is, using 3D finite element interface element geomechanical modeling, they were able to choose an optimal injection rate, and with this optimal injection rate, see what the effects on the surface and subsurface would be over time. And what they found was, for their optimal pumping rate that was chosen to be 1 million metric tons of CO2 per year, that after 4 years there was a risk of ground surface uplift and also a likelihood of formation of shear failure in the formation. And then after 7 years, there was a likelihood of the formation fracturing from overpressure, and also after 7 years, there was still no risk of cap rock failure. So while considering these results and also the initial overpressure state, they concluded that at this pumping rate, they could safely inject CO2 for 2 or 3 years before failure was likely from tensile fracture.
So the second case study is the Insula CCS project located in Algeria. And so this project was on the anticlinal Kretschmer Formation, which has a capacity of 17 million metric tons in its reservoir. And the reservoir is 20 meters thick and about 1,800 meters deep below the surface. Also, there are multiple cap rock layers in the Kretschmer Formation that consist of sandstone and mudstone that keep the CO2 from migrating upwards towards the surface. The Insula CCS project began in 2004 and was suspended in 2011. And in between this time, 3.8 million metric tons of CO2 were sequestered successfully. However, there was an unexpected increase in pressure in the lower cap rock, which ultimately suspended the project in 2011. So the CO2 that migrated into the lower cap rock, which is located right here, was caused by migrated into the lower cap rock through secondary porosity. Secondary porosity are the larger cracks within the material instead of the porosity within the material. And so evidence that suggests this suggests that there was a higher pressure in the lower cap rock was found by INSAR imaging and leak-off tests. INSAR imaging determines the minute changes in deformation on the surface using satellite imaging. Leak-off tests pump fluid down into wells and determine the fracture stress associated with that material. And so, in conclusion, the reason why CO2 migrated into the lower cap rock was caused by high injection pressure, which exceeded the leak-off test fracture determination, and also that the vertical hydraulic fractures allowed a pathway for the CO2 to enter the lower cap rock. As you can see, the vertical hydraulic fracture right here pushed material out to the side and also formed a double lobe surface on the surface. This can be seen in the INSAR image right here, where the double lobe surface deformation can be seen through INSAR. So the conclusion of this case study is that the CO2 migrated into the lower cap rock caused by hydraulic fracturing and second porosity.
The third study we looked at dealt with enhanced oil recovery. As I mentioned before, enhanced oil recovery first used CO2 in the 1970s. In the 1970s, when it first began, the goal was to maximize the amount of oil recovered while also minimizing the amount of carbon dioxide that was injected. But now, as we're looking to carbon sequestration as a means for reducing our emissions, the goal has changed a little bit. It's not only to maximize the amount of oil that's recovered, but also maximize the amount of carbon that remains in the reservoir after injection. So this particular study in southwest Iran looked at 3 different scenarios for enhanced oil recovery. The 3 different scenarios were natural depletion, water injection, and then carbonated water injection. And what the results showed was that the carbonated water injection performed the best and led to the highest ultimate recovery of the oil. It recovered 36% of the original oil in place, compared to 21-30% for the other two methods. So not only is this an efficient means of recovering oil, but additionally, 75% of the injected CO2 was able to be stored in the reservoir at the end of the experiment. So while this is very promising, there are still further research. There is still further research needed to determine the effects of carbonated water on the minerals.
So a summary for CCS is that carbon capture and sequestration is a three-step process, which involves the capturing of CO2, the transportation and storage of CO2. So as found in case study number 1, modeling and prediction making is key for determining future situations. The second case study involved the failure of the lower cap rock, which allowed CO2 to migrate into the lower cap rock, caused by hydraulic fracturing. And the last case study is the use of CO2 for enhanced oil extraction and also storage.
So to conclude, we believe that carbon capture and sequestration is a viable option for CO2 reduction worldwide. However, before CO2 can be injected, as determined from our case studies, the rock characteristics and additionally the thorough site analysis needs to be performed to ensure the safety and stability of the formation during injection. Also, it's very promising that CO2 can be used for both enhanced oil recovery and CO2 storage, kind of killing two birds with one stone. But the technology as a whole is still relatively new and does need to be developed a little further to ensure safety and before we can see it as a awesome option. Thank you. Do you have questions?
Cool.
I wonder how long it was.
13